Hello, this is a walkthrough for the Fall 2016 Exam 1 for Calc 3. I'm going to try talking a little quieter in this recording because you may have noticed, and I sure have, that the microphone that I'm using makes little popping noises every once in a while, and I'm pretty sure that's because I'm talking too loud, or at least I have a hunch that I can reduce the amount of popping if I just talk a little quieter. So, I don't know. Let's get going. Let's find an equation of a plane containing these 3 points. Well, we should try to kind of visualize that to start off with. If we have, well, let's actually build up to it. If we have 1 point, you can kind of let's try. If you pin your hand at 1 point, you can rotate your hand an infinite number of ways around that point. There is no one plane that contains that point. Similarly, if we have 2 points, now we've restricted one of the dimensions you can rotate your hand in, but you can still rotate around, the axis formed by these 2 points. But the minute we add a third point, that's kind of you can draw a triangle between these. That triangle will also be within the plane, and it's that angled surface that we are dealing with. So the 3 points we have 1, 0, 0, 3, 2, 0, 0, 2, 1, and their space on the page has nothing to do with what the values of these points are. Let's see, we know that if we want to find the equation of the plane containing these points, we can take the cross product of the vectors pointing from one of these points to the other 2 points, and we will get, well, in this case, visually, it would be a vector coming directly out of the page, or a vector going directly into the page. It doesn't matter either way. So let's figure out what these vectors are. This first vector is going to be 2, 2, 0, and this second vector down here will be -1, 2, 1. So let's cross these. 2, 2, 0, -1, 2, 1. We're going to get 2, -2, 6. And we can put this into an equation of a plane. We have 2x minus 2y plus 6z, and we'll just simplify this down, 3 and 1 and 1, and then that's equal to some constant. And that constant is going to come from any of these points. It will satisfy any of these points. So if we plug in 1, 0, 0, we see that our constant is 1. If we plug in 3, 2, 0, we will also get 1. And that's kind of the definition of this equation here. It's an equation that is satisfied by any of the possible points that we could put on this plane. So there we go, and that is answer choice. Whoops, that's the eraser. That's answer choice B. What is the angle in radians between the planes, this guy and this guy? Okay, so we know that the angle theta between two vectors is going to be the inverse cosine of, let's call this vector A and this vector B, A dot B over magnitude A multiplied by magnitude B. And this comes from the definition of the dot product, the formula for the dot product. The thing is, we're dealing with 2 planes, but the same can be true here because we can pull a vector out of each of these, which is the normal vector of the plane, and I hope you can kind of tell intuitively how the angle between these normal vectors is the same thing as the angle between the planes. Let's say we had 2 planes that were parallel enough so we could kind of draw them like this, and we're kind of looking, these planes are coming up out of the page at us. Hopefully, and I'll make them not at a right angle, hopefully you can see how this angle theta in here is the same thing as the angle between the normal vectors there. We're getting the exact same angle, and this is a little bit of a confusing way to draw it, but hopefully that makes sense to you. So let's pull out these vectors. We have 3, 0, -3, coming from our first plane, and 1, -1, 0. Okay, so let's start figuring this out. We have theta equals cosine negative. That does look like a q, doesn't it? Not a theta, but I promise it's, at least I meant it to be a theta. Okay, so our dot product between these two vectors is going to be 3. The magnitude of our first is going to be root 18, and the magnitude of our second is going to be root 2. And so we multiply these together. This is root 36, so 6, which is the same thing as 1/2. There we go. And the inverse cosine of 1/2 is pi over 3. Okay, which of the following equations produces a surface that is not shown here? So all we're really doing here is matching up the memorized equations that you just should have kind of on demand in your head for our quadratic surfaces with, the surfaces that they're giving to us. So let's just go through for the sake of practice and label these. Actually, I'm not going to write them out. I'll just say them because writing out hyperbolic paraboloid, which is our first one here, we have a hyperbolic paraboloid. Writing all that out is, I can be lazy to a certain extent here. Okay, then our second one is an elliptic paraboloid. Then we have an ellipsoid over here and a cylinder. And a cylinder is really not a quadratic surface. It's not one of the ones that is on our quadratic surfaces list, but it's still a surface. I guess it's not quadratic in some way, whatever, but that's still there. So we're looking for these four equations. Well, the equation for A is the equation for a hyperbolic paraboloid. The equation for B is the equation for an elliptic paraboloid. The equation for C is the equation for an ellipsoid. And let's see, the equation for D is a cylinder. We do not have a hyperboloid of 2 sheets in there at all. And I highly doubt that they will ever ask this kind of question and, try to get you to determine differences between the coefficients that they give you. Like I highly doubt they'll give you 2 options for ellipsoids, one of which is this and one of which has different coefficients. I don't think they're out to get you that much. Let ABC be the point of intersection of the space curve. It's always makes me feel cool when they say space curve. I don't know why. R of t is all of that, vector value function with the surface missing. So this is a little bit of a cryptic question. It's unclear what they really want you to do, but in the end, it's actually a lot easier than you would think. So we know that when our curve intersects our surface here, we want the x-coordinate of our surface to match root 2t, and the same goes for the y component matching y over here, etc. So all we have to do is substitute in root 2t for x over here, t squared plus 1 in for y, and so on. So let's do that. We will get 2t squared plus 2t squared plus 2 minus 1 plus 4t equals 0. This will give us 4t, that's a terrible square root, 4t squared plus 4t plus 1 is equal to 0. And if we factor this, let's see, oh God, I'm bad at factoring this kind of thing. Let's see, 2t plus 1. Wait, that just works, doesn't it? Yep, that does. Okay, so we see that our curve only intersects at t equals -1/2. Okay, that's good. And we are told that ABC is this point of intersection. We know that at this point of intersection, A is going to equal root 2 times our t value, which is negative 1/2, that b will equal t squared plus 1, so 1/4 plus 1, and that c is going to equal 1 minus 4, 1 minus 4 times negative 1/2. Okay, let's simplify all these out. This will become positive 2, so the whole thing down here is 3. This is 5/4. And over here, we are going to get negative root 2 over 2. And things are still looking pretty scary, and I'm actually concerned that I might have done something wrong, but let's just see. A squared plus 2b, that's going to be, well, negative root 2 over 2 squared is going to be positive 2/4, so 1/2 plus 10/4, which is 5/2, so we get 6/2, which is 3. And so 4 is hopefully A. Thank God. Let's find the length of the curve r of t given there on the t between 0 and pi, and we're told to use this double angle formula. And if I remember correctly, the double angle formula comes in a very weird way. So let's see if I can remember how this goes. So we know that our equation for arc length is the integral, well, in this case, I'll just put our bounds in, but we're integrating from 0 to pi times the magnitude of r prime, not times, just our integrand is the magnitude of r prime of t dt. So let's find r prime of t. That is going to be 1 minus cosine t, and then sine t. And the magnitude of this guy is going to be the square root of 1 minus 2 cosine t plus cosine squared t plus sine squared t. And that's equal to magnitude r prime of t. Okay. Immediately we can see that we can replace this cosine squared and sine squared with a 1. I'll just bring that over here as a 2. Awesome. So it's coming back to me. I think I remember what we're meant to do here, and it is a little weird because we can apply this double angle identity even with just a normal t. All this equation is doing is, if we go this way, is taking whatever we have in here and dividing it by 2, giving us that x from the 2x that we started with. So in our case, this cosine t is going to become 1 minus 2 sine squared t over 2. And so we can substitute that in. And this is going to become the square root of negative 2 times 1 minus 2 sine squared t over 2, need another parentheses there, plus 2. Okay, so we can see right off the bat that this little section here is going to become a negative 2, which is going to cancel out with our positive 2, and this is going to become a 4. Now we can take our square root, and this is just going to become 2 sine t over 2, r prime t. There we go. Yeah, that kind of deserves a drum roll. It's one of the weirdest things that they have had us do with trig in a good long while, which is saying a lot because it wasn't actually too bad. It's just kind of, you can't really look at the equation in the form that you get under the square root and kind of think of that right off the top of your head. So now everything's easy. We're integrating from 0 to pi and our integrand is 2 sine t over 2. dt. This will integrate and give us negative 2 cosine t over 2. And let's see, do I remember how to integrate? It has been 4 months since I took this exam last. Let's see. Holy crap. Yeah, 4. There we go. And this is extremely pathetic. I'm going to make sure, though, this is going to become 2 cents. Okay, yes, good. I still can integrate. And see, the thing is, I could probably do spherical integration fine, but this stuff is, okay, I'm getting off task. So negative 4 cosine pi over 2. Well, cosine pi over 2 is going to be 0. So this whole thing's 0. And the cosine of 0 is going to say negative 4. Our answer is 4. Awesome. The curvature of the curve r of t is that thing at t equals pi is what? So this is interesting. The equation that I like to use for curvature, it's always some weird little k that they draw, is v cross a over magnitude v cubed. So you might be a little worried pulling out this equation because you might remember that the cross product is only really defined in 3 dimensions, and we're dealing with a kind of 2-dimensional path. But really, all we have to do to put this into 2 dimensions is say that put it into 3 dimensions, is to say that r of t is 9 cosine t, 9 sine t, 0. And so that's kind of, expanding our view into 3 dimensions without actually changing what's going on. So let's find our r prime of t, which is v of t, and that's just going to be negative 9 sine t, 9 cosine t, 0, and our r double prime of t, otherwise known as a of t, our acceleration, is going to be negative 9 cosine t, negative 9 sine t, 0. Okay, let's take these cross products. So our first cross is going to give us 0. Our second cross is also going to give us 0. And our third cross will give us 81 sine squared t plus 81 cosine squared t. And we know that this can just simplify down into 0, 0, 81. Okay. Oh, and look at that. I messed something up from the very beginning. Sorry about that. It's magnitude v cross a. That makes a lot more sense. So now we have 81 on the top. We're looking for the magnitude of v cubed. Well, the magnitude of v, if we're just looking here, well, that vector at all times is going to have a length of 9. So our magnitude is 9, so we're looking at 9 cubed. And really this is 9 squared up here, and so our answer is 1 over 9. Okay, question 7. We're given a classic particle motion question to solve where we're given acceleration and we're going to have to integrate down all the way to position, adjusting with our initial values that were given along the way, and it's going to be a good time. So let's integrate a of t. We will get 2t, and then we have to make sure that that component agrees with v of 0, and it looks like it doesn't, so we'll need to add 1 so that when t is equal to 0, x is equal, or x component is equal to 1. Then over here we will get negative sine t, and that does agree when t is equal to 0. And then finally 3/2 root t, and that does agree. So this is our v of t. And then finally, well, not finally, penultimately, I guess, we are going to find our r of t, which is just, again, integrating v of t. So we'll get t squared plus t. And now we're taking a look at this initial value, and that does agree when t is equal to 0 for our x component. Here we're going to get cosine of t, and when cosine of t is 0, when t is 0, cosine of t is 1, so that does agree with our initial value. And then finally, t to the 3 halves, and t to the 3 halves when r is equal to 0 does not agree, so we'll need to add a 1 there to compensate. Okay, so finally, all they want us to do is plug in t equals pi, and we will get pi squared plus pi, -1, pi to the 3 halves, plus 1. And our answer is answer choice A. Let's consider this function on its maximal domain of definition. Calculate this limit right here. It looks like I have a little, oh, there we go, it disappeared. Okay, let's calculate this limit. This question is a great example of how it's super easy to overthink one of these limits. When I was taking a look through this exam right before I took it, just to make sure there weren't any, big traps that I didn't want to fall into on recording and then have to go back and fix. I took a look at this problem and and I said that the limit did not exist. And I did that because I didn't really look at the function up here. I jumped straight to the, it's easy to go into these problems with the presumption that the limit likely does not exist, and to just miss easy things. So the first thing you should always do when evaluating one of these questions is plug in the values that it's approaching, usually at 0, 0. Let's plug in 0, 0. And what do we get when we plug in 0, 0? We get 2. And just to check, because, thank you. Okay, good. Just to check, because it would be hilarious if I still got it wrong. Yeah, it turns out that 2 plus 0 over 1 plus 0 is actually equal to 2. Here's where the real stuff starts happening. Okay, so we have a function p, which is a function of u, v, and w, and then u, v, and w each are respectively functions of x and y. Okay, this is a multivariable chain rule question. We're looking for p of x when x equals 0 and y equals 1. It's important to recognize that those aren't u, v, w coordinates there. So px, by the formula that we have for the multivariable chain rule, is going to be pu ux plus p v vx plus pw wx. And just like all these problems, even though this one is a good bit more annoying than usual, all we have to do is fill in all of these blanks that we have here. Really the hard problem about this question is the way that they format it. If they had put this in a table, it would have been fine, but it's a real pain to read what's going on here. But we can start to fill in things already. We see that ux at 0, 1 is 2. There we go. Let's see, we see that wx is 0, so that gets rid of this entire bit of the expression. And let's see, we can find vx. Vx is just going to be y e to the x. And when we plug in our values, vx is 1 e to the 0, or just 1. So let's put that in there. And finally, let's find pu and pv. So this is just going to be u over root u squared plus v squared plus w squared. and v over root u squared plus v squared plus w squared. And we have our values for these. U is equal to 0 when x and y are equal to 0 and 1. V is, well, y e to the x, which we already said is just 1. V is equal to 1. And w is equal to 2. It's important to recognize we can go simplify this even further because we see that u is 0. So this entire thing right here is equal to 0, and we can get rid of this part of our expression. And all we're left with is PV. And PV we can solve. That's going to be 1 over the square root of 1 squared plus 0 squared plus 2 squared, so root 5. And so our answer is 5 to the negative 1/2. Awesome. Okay. The total surface area of a cone having height h and base radius r is all this stuff. R and h are measured to be 3 and 4 inches respectively, but those measurements could be off by 1 inch each in either direction. So this is one of these questions that if you feel so inclined, you can do absolutely zero calculus and just get through all of the arithmetic and actually get the right answer, as long as you have the intuition to realize that just like I'll rephrase. As long as you have the intuition to realize that, let's give a little visual. A square of radius, of side length 1 is going to have an area of 1, but if we increase that, let's say we have a square of side length 2, we now have an area of 4, and let's say 3, 9. So you can see that there isn't a linear relationship. Every unit that we increase in side length, we're getting a lot more out of our area function, and that works the same way for a cone. And all that really means for us, if I get rid of all this crap, is that if we measure our cone to be of radius, what did they say? 3 and height 4, we're going to get a larger error if our cone was actually, doesn't even look like a cone, but if our cone was actually of height 5 and radius 4, that's going to give us a much bigger error than going back the other way. And so you could just go in and plug 4 and 5 in and then subtract out plugging 3 and 4 in, but we'll do the actual differential stuff. So I like to think of this, and this is really not the way we're taught, it's the way I kind of taught myself because I didn't learn differentials when they were taught. I don't know why. It was a mistake on my part. So we have this error function, and this error function is made up of AR delta R plus AH delta H, where these delta R's and delta H's are the possible changes, so the maximum error in measurement, and in this case, that's 1 for each of them. We're told that right here. And then these ARs and AHs are just the partial derivatives of A with respect to R and H. So let's find those. AR and AH. AR, this is the more complicated one. This is going to be pi root R squared plus H squared plus pi R, and then the derivative of this guy, which I'm having trouble with right now, and that's going to be, let's see. R over the square root of r squared plus h squared. Okay, I hope that's correct. And then plus 2 pi r. And then finally our AH is going to be just pi r times h over root r squared plus h squared. Okay, let's see if I actually did remember my Calc 1 material, because all we have to do now is plug in 3 and 4 for AR and AH, add them together, and we should have an answer. So 3 squared plus 4 squared, 9 plus 16 is just going to be root 25, and so all of these guys are going to, all of these square root expressions are going to turn into 5. So AR is 5 pi plus, let's see, pi r squared over 5, so pi times 9 over 5 plus 2 pi r, which will be 6 pi, and then AH is just going to be 12 pi over 5. And now all we have to do is add these two together, except this is a little bit of a pain, so bear with me. We'll have 25 pi over 5 plus 9 pi over 5 plus 30 pi over 5 plus 12 pi over 5. Oh my god. 25, 9, 30, 12, 14, 16, 76. 76 pi over 5. And let's see, 75 over 5. 76 over 5. I'm going to see. Okay, yes, I may or may not have just typed that into Google. I'm feeling a little lazy tonight, but our answer, thank God, is 15.2. 15.2 pi. I'm sorry you had to bear with my kind of failures on that one. Okay, so r of p and q is the inverse tangent of pq squared, and we're meant to find the mixed partial derivative. We can also write this as r pq or r qp, because remember, the mixed partial derivative is always the same no matter which order you do it in, at least for the normal functions that we're dealing with. I'm pretty sure that's Clairaut's theorem or whatever Kaufman said last semester. So we know that the derivative of the inverse tangent function is 1 over 1 plus, or sorry, I'll be more clear. Dx of tan negative 1 x is just going to be 1 over 1 plus x squared. And so we can apply that here, where well, we're taking a partial derivative, so I'll be clear. Partial p, I guess we'll do p first, of tangent negative 1 pq squared. And so this will give us 1 over 1 plus pq squared, quantity squared, multiplied by, because we have to apply the chain rule, q squared. And that does not really look like a q. Sorry about that. P squared, q to the 4th. Okay. And finally here, we have to apply partial q to q squared over 1 plus p squared q to the 4th. And this is going to give us, 2q times 1 plus p squared q to the 4th minus q squared 4 p squared q to the 3rd, all divided by 1 plus p squared q to the fourth quantity squared. Okay, let's start expanding our numerator here because we can simplify this pretty drastically. So our numerator is going to turn into 2q plus 2p squared q to the fifth minus 4p squared q to the fifth. And all this is going to do is simplify down to negative 2p squared q to the fifth all over quantity 1 plus p squared q to the fourth squared, which is answer choice B. Let's find the directional derivative for t of x and y that's given there at 3, 2 in the direction of the origin. So we know that we are going to need our gradient vector for a directional derivative, and that's just going to be the vector of tx comma ty, and we're going to be dotting that with the unit vector of the direction that we are pointing in. In this case, our direction is towards the origin, and if we're sitting at the point 3, negative 2, our vector towards the origin is exactly the opposite way we came, so negative 3, comma 2. Negative 3, comma 2, but that's not a unit vector. We need this as a unit vector, so we need to divide by its magnitude. Its magnitude is root 13, so 1 over root 13 needs to go out there. Now finally finding tx and ty should be pretty easy. Tx will be 1 minus y over x minus 2 squared, and ty is going to be 1 over x minus 2. And since we know that we're at the point 3 comma negative 2, this is going to give us 3 over 1, and over here we will get 1. So tx is 3, ty is 1. We're taking this dot product. We are going to get negative 9 plus 2, so negative 7 over root 13. And that is it for that. I hope that was helpful, and I'm going to go to sleep in a little bit, or at least go do some other work. Okay, see ya.